Recording. All right, I think we're good. So we were talking. I brought actually the slides from previous class just to go over them fast, and because I want to do two more examples, go over two more examples. So we're talking about motion in a straight line, right? Pretty basic definitions: velocity, acceleration, and then the relationship between velocity and acceleration, right? Aside, well, two relationships between velocity and acceleration, aside from derivative of velocity with respect to time, which becomes acceleration. We also have ADS equals VdV. That comes handy. If you remember, we actually use that to derive. That can give us an extra equation to deal with the number of unknowns that sometimes we have to work with. You will see more about this later on when we start talking about motions on curvilinear motions, motions on paths or lines that are not straight. You see the variation of that in angular, or better to say in rotation. So that becomes alpha, and then V becomes omega. We'll talk about that. Now, we said that to make it a little easier to deal with different types of problems, we're going to classify them, or we classify them in four groups. We said that acceleration can be a function of time. If it's a function of time, we derive the relationship between velocity and acceleration, position and velocity. I remember we said all we want for now is we want position, velocity, acceleration. We want to be comfortable and we want to be able to go from one to another. So to be able to do that, we're just classifying the problems based on the type of acceleration we might have to deal with. And also in terms of graphs, I said, well, velocity is basically the area under the curve, acceleration time, and position, which actually you can even think of that as displacement, the difference between the final and initial position, is the area under velocity time curve. I went over an example, go over it again. I will go over it again. Then we said the acceleration can be constant. Well, these equations probably you have seen even way before dynamics, maybe somewhere in physics, the relationship between velocity and acceleration, position acceleration, velocity and acceleration, when acceleration is constant. Acceleration can be a function of velocity. That's a little more tricky. And eventually acceleration can be a function of position, right? Depending on what we're dealing with. I said the good examples for these are the one good example is the spring. Probably have seen in statics what the force of a spring is. You know, spring stiffness multiplied by how much is stretched or compressed. Over there, the acceleration basically you can think about it as a function of position. All right. I went over one example again. Another example that basically talks about acceleration as a function of position. We use the relationships we derived for acceleration as a function of position. I believe that was pretty straightforward. We got the final velocity. So we had acceleration as a function of position, and we had some initial, not initial, final numbers. We know where in this case a car is located. We know S naught. We know its initial velocity, and we know where it's located at the end of the motion, so we could find its final velocity. All right, so let's go over two more examples. One very simple, and another one still simple, but I guess it's a little longer. So this example says we have again an airplane. In this case, releases its drag parachute at time equals to 0 second. Right, so it's the reference initial moment is 0. That's where we start measuring everything. Its velocity is given as a function of time by v is equal to 80 over 1 plus 0.32 t meter per second. Now the question is, what is the plane's acceleration at t equals to 3 seconds, right? After 3 seconds of motion? Well, this is a very simple example. So we know velocity as a function of time. We basically just have to use the definition of acceleration. Definition of acceleration, derivative of velocity with respect to time. Right? That's all we need to do. dv dt. You have to take derivative of this fraction. Hopefully you remember to do that, or remember how to do it. Derivative of numerator, which is basically 0 multiplied by denominator, minus the derivative with respect to time of the denominator, which is 0.32 t, which becomes 0.32, times the numerator, which is 80, divided by denominator squared. Goes back to the derivation of, hopefully you remember that. I don't know, let me just make sure that u over v, I can write it, I guess, this way as just a reminder. Don't get lost there. So that's pretty much dt u over v would be right. Du dt times v plus, right? Let me see if I can write it. No, I can't write it better. Du dt times v minus derivative of numerator times denominator, and then minus derivative of denominator times numerator dv dt u divided by denominator squared. I don't know who doesn't remember this, but just in case. All right, this becomes, if we do the multiplication, this becomes a minus 25.6, and denominator just stays the same, t squared. So we are told that at what time we want the acceleration. Well, now we know the acceleration is a function of time. All you got to do is just to replace that value, t equals to 3 seconds. You get a as, I can just give you the final number, minus 6.664 meter per second squared. The ones who know me know that rule number 1 in this class is always to check Maslows' number. Make sure that the procedures usually are good. I can assure you that, but numbers, I highly encourage you to double check the multiplications and the final answers. All right, so this is pretty straightforward, right? Nothing really weird there, hopefully. Having said that, if you have any question, actually just ask and stop me here, or if you spot something unusual. All right, let's see. Let's do something a little more fun. Let's do any question on this one, right? Just pretty much the definition of acceleration. You don't really have to go that far. Now, examples I do in class are mainly coming from problems at the end of that section of your textbook. So I usually leave examples in your textbook for you to actually practice as extra examples. Examples in class are coming from the problems at the end of that specific section we're covering. So this way you have some solved problems and you have examples in your textbook that are pretty well explained. So you can use, you're going to have more examples and problems to work with, solved problems to work with. All right. Let's do the next one. Now, the next one, we have, actually we are given the acceleration as a function of time in the form of a graph. So let's just do one of these because that's also something you'll see. The graph shows the airplane. I don't know, there's some, I think the authors of this textbook are aerospace engineers. So you'll see a lot of examples related to airplanes in the textbook and some good number related to robotics. So somewhere between aerospace and robotics, these two fields are the focus of the authors of this textbook. So you'll see a lot of those kind of examples. Airplanes, acceleration during takeoff. Let me draw the graph here. So this would be time. This would be acceleration. So A as a function of time. To put units, I usually don't do that, which is not a good practice. Then we have straight line right there and horizontal line right here. This would be 1, which is meter per second squared. And this is 4. This point time is 5 seconds. And all the way at the end, you'll get 30. We know the unit is seconds, so I'll just put 30 there. So this would be 30. So this is the airplane's acceleration during takeoff. Right? It starts from, let me add that. It's during takeoff from the moment it starts moving. Now, we're asked to find two things. A, we're asked to find what is the plane's velocity when it lifts off at t equals to 30 seconds. Let's find this one first, then I'll put the second one, the second part. So we have a graph representing acceleration as a function of time, right? We know the initial acceleration, then acceleration is increasing as a function of time. And then the acceleration is constant. After 5 seconds, the acceleration is increasing as a function of time. T equals to 5 seconds. When acceleration reaches 4 meters per second squared, then it's just constant. We're asked to find the velocity when it lifts off at 30 seconds. What was the velocity? We have a graph. If I go back to acceleration as a function of time, all the way right here. Right? If you look at the left kind of graph that I put there, or schematic of a graph, we have acceleration as a function of time, and we already said that, well, that equation, that integral, is nothing but the area under this curve. So from the initial moment, t naught, whatever it is, to the final moment, t, if you want to find how the velocity changes, right, all we need to do is we have to find the area under the curve for acceleration time graph. So I'll do the same thing here. So how do I do it here? So I have two areas. Right? There's this one from 0 to 5. Then I have this one from 5 to 30 seconds. Right? So what does that give me? It gives me the V minus V naught. Right? We said it from there. V minus V naught is equal to area under the curve. So what is the area under the curve? We can do it in different ways. You know what? I'll leave it to you. Can someone tell me what is the area under the curve? Just as a review. So we have, go ahead.
Like the integral of the function?
Well, we can do the integral, but that's the hard way, right? We already have the shape and we have all the numbers. So think about more like geometry. You want to find the area of a rectangle, triangle, and that shape on the left side. Craig actually is, that was very fast, Craig. Yeah, it is 112.5, but how did we get there? So let's call this 1 and call this 2. For 1, well, straightforward. It's basically just the multiplication of the sides. It's a triangle. Sorry, it's I don't know why it's a triangle. You know, this side is 25, right? 30 minus 5. So 25 times the other side is 4, right? So that would be 100. And this side, for number 2, we can actually, if you remember the equation, you can find the area for number 2 directly. But if you don't remember that, and you're like me, I have a very short memory. Don't keep things in your memory for too long, especially old knowledge. You can just break it from this line, and then you're going to have 5 by 1 and plus some triangle up there. So let's see if we can follow this. This is going to be 5 times 1 plus, this for this triangle. So I'm breaking down number 2 to 2 geometry, right, to 2 shapes. 5 by 1, and then I have 5 times 3 divided by 2. It's basically, I'm just finding the area under the curve. So if I put everything together, this would be area 1 plus area 2. This becomes 112.5, as Craig mentioned. Now, here is the thing. We are asked to find, well, first, did this make sense? If you have any question about this one, right? Again, very old knowledge. I'm almost sure that all of you know how to find areas. But it's just a reminder that keep an open mind that when you're given the acceleration as a function of time, you don't have to deal with this integral and take the integral and find the line, the equation for the line. It's all complication. If you just want a velocity, you can just easily find the area under the curve. Now, this is V minus V naught, right? What I'm asked to find is what is the plane's velocity when it lifts off at 30 seconds, at t equals to 30 seconds. should be t equals to 30 seconds grammatically. So I'm looking for v. How do I find v? Right, this is v minus v naught, the area. Right? From initial moment to final moment, the velocity difference is, we said, is the area under the curve. Now, what is the final velocity at t equals to 30 seconds?
I don't know if this is right or wrong, but I remember that if you take the slope of the AT graph, wouldn't you get the velocity, like the final velocity? I think.
Well, okay, so you're into something, but the slope of position time gives you velocity, right? Not, and then the slope of velocity time gives you acceleration, but not other way around. We already have acceleration as a function of time, right? Now you have to take a look at the problem statement, always in detail. Right? It says from the moment it starts moving. So this graph gives you the story about the motion of this airplane from the moment it starts moving. What does that mean?
That means v naught is 0.
Exactly, Justin. Exactly. And as I said before, rule of thumb, when you don't know what is the initial velocity, acceleration, usually it's 0. Don't quote me on that, but always try to look at the problem statement. Right? Somewhere they're hidden, it gives you enough information to figure these things out, the initial conditions out, if you're not given directly. Right? But yes, as Justin mentioned, it starts moving. So this graph basically is the story from the beginning. So v naught is 0. So your v pretty much is 112.5. So v is equal to 112.5 meter per second, because this is 0. I'll just put it here, v naught is 0. All right, so first one was relatively easy. Now the second part. Any question on this one? All right. The second part is asking you to find the position. Right? So the second part says, what is the distance? What is the distance or let's just phrase it like the problem statement. What distance has the plane traveled when it lifts off at t equals to 30 seconds? This is a little more tricky. This is a little tricky because you have acceleration over time, right? But seems like area under the curve is not going to help you anymore, because area under the curve only gives you velocity. So what do? Go back to acceleration as a function of time. What are options? So we have to actually deal with those integral form equations now. We try to avoid using them, right, for the first part, but now there is no other way than using those equations. We have two, right? We can find velocity knowing the acceleration as a function of time at any given time, and we can find position as a function of time, knowing velocity as a function of time. All right, so here's what we're going to do. Keep in mind that we have, if you look at the graph, acceleration as a function of time, we have two parts in this. The first part is motion from 0 to 5 seconds. In that part, acceleration is a function of time, right? It's going up as a straight line, you can think about this as a line and think about this axis, these axes, x, y axis, right? If a is y and time is x axis, you know y as a function of x, right? It's just a line. As long as you find the equation of that line, you can find what is y as a function of x. It's just a function. Up to 5 seconds. At 5 seconds, now we're dealing with the constant acceleration. If you go back to case 2, constant acceleration. So we have 2 of these in one problem. Acceleration as a function of time for the first 5 seconds, then constant acceleration for time from 5 to 30 seconds. So I'll deal with them separately. Part 1, right, or from 0 to 5 seconds. All right, so I have to find v, or let's just be more complete. Let's say vt is integral from 0 to some time, given time. I want to find the relationship. I want to find the velocity as a function of time. At dt plus v naught. Oh, v naught we already established that is 0. Now here's the thing. I have to find at. I have the graph, but I don't know what at is. How do I find at? Acceleration is a function of time, to plug in that equation. Remember, we're talking about 0 to 5 seconds. So at the moment, all we're focused on is this part. This is what we're focused on. This is time, this is acceleration, and then you have a line like this. For this line, you know this is 1, you know this is 4, and this is 5. Let me make it a little clean there. So this is acceleration. This is the part that we're focused on, because that's the part that acceleration is a function of time and it's not constant. So how do I find acceleration as a function of time?
Because it's a linear equation, could you just use y equals mx plus b? So it'd be like 4/5 x plus 1.
Yes, the procedure is correct, and pretty much that's what we're going to do. But just a little change. Instead of 4/5, well, the change in a axis is 4 minus 1, so 3/5.
Yeah, you're correct. Thank you.
Exactly. Yeah, but yes, exactly that's what we're going to do. If you don't remember, pretty simple, straightforward, the way we write the equation for a line, right? I'm just going to put a reminder here. Let's say we know T naught, right? So let me see if I can put it as a general form. If you know X, Y, this is just a reminder for the ones who don't remember how to, if you don't remember how to write the equation for line X naught, Y naught, then you have Y1, X1. If you want an equation for this line, would be 1 minus y1, y minus y1 over is equal to, let's go with x1, y1, and x2, y2. Becomes y2 minus y1 over x2 minus x1, right, times x minus x1. Just a reminder that this is how we write the equation for a line when we know the beginning and end points for that line. And I'll do the same thing here. So you can think about this t and a as x and y. So this becomes a minus 1 is equal to 4 minus 1 over 5 minus 0 times t minus 0. So my equation, AT, becomes 3, or we can just put 0.6. 3/5, which becomes 0.6 t plus 1. This becomes my equation. And that's what I'm going to plug into here. And I'll take it right there and put it here. So this becomes from 0 to t, 0.6 t plus 1. Oh, my t looks like plus. 0.6 t plus 1 dt. And v naught is 0. We already established that. So all you need to do to calculate this integral. If you do that, well, this becomes what? This becomes vt is 0.6 t squared divided by 2. So it's going to be 0.3 t squared plus t. This becomes your v as a function of time. Now, once you know your v as a function of time, well, now you can use the second equation, right, for position. Now you know v as a function of time, so you can say s is equal to integral from 0 to some time t vt dt plus s naught. Let's go there. I'll go to the next page. So s as a function of t becomes 0 to t vt dt plus s naught. So I'm going to assume that s naught is 0 at the beginning. It doesn't really matter because I put the reference wherever I want. From the moment it starts moving, right, it's already set. So if we take that as s naught 0, we can find how much is traveled. Or we can take s naught to the other side and say we're actually calculating s minus s naught as displacement, because we're finding how much is traveling. So it doesn't matter where it is. You can look at it as this way. But I can just assume that reference is at s naught equals to 0. So st becomes integral from 0 to t 0.3 t squared plus t dt. Right, let's see if I did it correctly. It was 0.3 t squared plus t, exactly. Find this integral. This gives you st as the 0.1 t to 3 plus 1 over 2 t squared. This gives you s. Right? So now you know v and s as function of time. Right? This was for the part that acceleration is a function of time, for the first part. Now you can plug in t equals to 5 and find what is your acceleration. Well, you know your acceleration. What is your velocity and what is the position of the plane after 5 seconds of motion when acceleration is a function of time, right? At this point, exactly at the end of this motion right there, or you can think about it in this graph right here, you can find what is the velocity and what is the position. Now, why do you need velocity and position at that time and moment? Because the second part falls into the category of acceleration, constant acceleration. Now look at the equations. For these equations, for you to be able to find s, right there, right, this equation right here, you need to know what is the initial velocity and you need to know what is the initial position. Now, initial velocity, initial position for this section of the motion that the acceleration is constant is nothing but the final velocity and final position for the previous part of the motion, where acceleration is a function of time. So if you find the velocity and position at the end of that part of the motion, you use those as the initial values for the second part of the motion. Does that make sense? Hopefully it does. Let's do it and see how it goes. Right? So I'll need it. As a result, I'll just calculate that. I say at t equals to 5 seconds, right? I'll find v at t equals to 5 and s at t equals to 5. V at t equals to 5, I'll just plug in. That was 0.3, 0.5 squared plus, where did I put 0.5? 0.3 times 5 squared. I don't even need that. 5 squared plus 5. Right? And the displacement would be 0.1 times 5 to 3 plus 1 over 2 times 5 squared. You'll get the numbers as, for the first one, you'll get 12.5 meter per second. And for the second one, you'll get everything together. I believe you'll get 25 meters. 12.5 from the first one, 12.5 from the second one, meters. Now, this was for the first part, acceleration as a function of time. Now, second part, right, so from 5 to 30 seconds, that's where the acceleration is constant. All right, let me just, there you go. This one. And this one was here from 0 to 5 seconds. Now we are in the second part. Acceleration is constant, so it's much easier. Acceleration is constant, and we know what it is. It's 4 meters per second squared. Represented by a naught, because that's what we used to note constant acceleration. So velocity would be, just to remind you what we're using, go there, acceleration as constant. Velocity would be a naught t minus t naught plus v naught. Right? We don't actually need to calculate the velocity. Let's just go to position directly, because we're asked how much is traveled. So let's just use s. Now to find s, we need s naught, which we have it, was the final position at the previous phase. We need v naught, which we have it, final velocity for the previous phase. And we know we need a naught, which we have it. And t minus t naught, we also have it. It's 5 from 5 seconds to 30 seconds. Right? So let's just plug in everything. I'm not going to calculate velocity. It's not really asked. So s becomes 1 over 2 a naught t minus t naught squared plus v naught t minus t naught plus s naught. Right? So that becomes 1 over 2 times 4, 30 minus 5 squared, plus v naught, we got it as 12.5 from previous part, times 30 minus 5. This is just the time change. And s naught, we got it from before, plus 25. You do all the calculations. S becomes, the number would be 1,587.5 meters. That's how much the plane has traveled. Question on this one, Max. All right, so we split it into two parts for part B of the problem talking about. 0 to 5 seconds, acceleration as a function of time. Second part, constant acceleration. All right. Remember the velocity, the reason we calculate velocity as a function of time, because we needed that to calculate position as a function of time. If we didn't need that, we could find the final velocity. We could calculate the velocities from before, but there are other ways of doing that. But this is the best way of, I guess, doing this. And double check the numbers again. I did multiplications, everything by myself, so a pretty good chance there's something could go wrong. All right, especially the final number. Check that S. All right, so this was the last example I want to solve for motion on a straight line. Now, I'm going to also post a set of practice problems for you with the solutions for this topic, and that's where we are going to have our quiz for next Thursday. All right, that quiz is going to cover motion on a straight line. So go over the examples, the practice problems I'm going to post, and take a look at the summary and just double check your notes and make sure everything, the equations are right and everything is fine. All right. Any question on this?